addresses the XBee Series 2 radio again as used for remote data acquisition for a network of radios in API mode. So I've provided some commented Python code which allows you or any developer to acquire analog readings from an XBee radio within an API-based network. Now, the XBee Series 2 radio provides developers or users with 8 digital I/O channels or lines. They're labeled D0 through D7. 4 of them, D0, D1, D2, and D3, allow users to acquire analog as well as digital inputs. The final 4, D4, 5, 6, and 7, allow users to only collect digital inputs. Any of the D0 through D7 can be configured to generate digital outputs as well. For analog inputs, you'll have to look to one of the PWM pulse width modulated outputs, which we're not going to be using here right now. But we did use in one of the previous examples. So the next thing that I want to look at is a really good reference for AT commands that are recognized by the XBee Series 2 radio. And the reason why this is important is because these AT commands can be used to acquire as well as set different radio parameters that we've already talked about before, which allow us to manipulate a whole variety of network parameters. So, like I said a second ago, we're going to take a look at a great resource for the AT commands, which is this link here. I'm going to click on it real quick, if it will choose to cooperate. All right. And so you can find this resource online. I also saved a copy of it in my Dropbox, which is accessible to you. And you can see here, this is the XBee command reference table. So this shows all of the AT commands that you have accessible to you. And along with them, it also tells you what the range of values is, what the default value is, etc. So I often come back to this when I'm having questions about working with a certain parameter. Anyway, so we've talked about these a decent amount. I don't think there's any need to go over each one. Well, there's really not any time to go over each one right now, regardless. But which ones are we going to focus on for this example? We're going to focus on a couple of these. You'll see that several of the parameters, D0, D1, etc., are related to the digital I/Os, or analog and digital I/Os. And you can see that by setting the state, the parameter value, we can determine how it works. So mode 1 is a commissioning button enabled. We talked about the commissioning button before. 2 is going to be an analog input. 3 is going to be a digital input. 4 is going to be a digital output low. And 5 is going to be a digital output high. All right. And so we are going to use these in order to develop our code here. You can already probably tell, since we are looking to acquire analog signals, we are going to be using mode number 2. So now let's talk about some of the methods that we're going to need to use. One of them is DDO set param. So one important function provided by the ZigBee library is the DDO set param function, and hopefully you can see the similarity to our DDO get param function. DDO get param was used to acquire parameters, and DDO set param is going to be used to set parameters. And this section of the document is going to examine how the function is used. So here's the general structure. We have DDO set param, the address, the extended address, the ID, value, timeout, and then additional inputs, order and apply. And then it returns a Boolean value, potentially, well, not potentially, it indicates whether the set was successful or not. It does provide some feedback in that regard. So let's look down here, and you can see what I've done is create bullets to essentially tell us how each input is used. Okay, so let's look through them. This function allows the user to define a given parameter of an XBee device. It employs the following mandatory input variables. So these three are mandatory, which I'll just put an M there. All right, we have address extended. It's a string such as this form right here that must include brackets and the exclamation point as shown, so be careful of that. It defines the address of the device to be controlled. Pretty straightforward. ID. This is a 2-byte string, such as D1. The mapping between the IDs and functionality is determined by the specific device's firmware. As such, one must obtain this information from product documentation. Okay, and what we're going to be using for our base radio is going to be these AT commands. So some other devices may have additional commands on top of these. However, we, for right now, are just using the stock XBee radio Series 2, and so the values, the IDs, I should say, that we will have available to us will be those that were listed in that reference document. Okay, so we've dealt with that one. Next, value must be either a string or an integer. Some commands do not require value. So if you're talking again about our D0 ID, you'll see that the potential values it can take on are 1, 2, 3, 4, 5, and in that case, you would be passing an integer. Sorry, I drew the arrow to the wrong spot. You would be placing an integer or supplying an integer to that input. Now, the other three are optional input variables. So I'll put an O here for optional. Timeout is an optional parameter that defines the time that the method will wait for a response before timing out. Order defines whether this command should be processed in order relative to other commands and data transmission. So if you set it equal to true, it'll do that. This may significantly delay processing of commands. However, order equals false may result in an out of order command execution. So you have to figure out which is more important to you. Is it speed or is it, let's say, ordering, or I would almost say functionality, right? Because if the order of the commands is out of whack, then you're going to be altering the functionality of your application in some probably undesirable way. Now, if you're not talking about quick actions, meaning that they don't follow each other back to back very quickly within fractions of a second, you're probably not going to have a problem with ordering. So if you're doing one action every 5, 6, 10 seconds, I would think that it would be able to process everything fast enough such that it wouldn't really matter which one that you used. Okay, apply defines whether changes should be applied to the node immediately. That's where you define it true. If you set it equal to false, then changes are queued in the node until a command with apply equals true is executed or the AC command is executed. Let's take a look in here real quick and see if we can find the AC command. All right, there we go. Great. So the AC command, you can see here, apply changes. Applies changes to all command registers, causing queued command register values to be applied. And then, you can see where it goes from there. Anyway, so you have two choices. You can either apply your DDO set param where here apply equals true, or you can set it equal to false or negate defining it. That's another option. Remember, you have three options. And if you take two of those three options, meaning setting it equal to false or not defining it at all, then you will not have your change applied until you either call that same DDO set command again with apply equals true, or you call the AC command, apply changes command. So be cognizant of that, because this could be one place where you're questioning yourself, well, why aren't my changes working? And it could be something as simple as needing to apply the AC command there. All right, so the DDO set param function returns a true or false based on whether the remote node accepts or rejects the set command. It's advised that all DDO set param statements be wrapped with a try except loop, and right, that would be for exception handling, right? You want to be able to provide either an opportunity for the system to retry the transmission or to convey some sort of message to the user about its status, whether it succeeded or it failed. All right, let's jump into the Python code for data acquisition. The name of the script is access xbee solo.py. I developed it, and this is, I think, one of the more interesting examples. It's one of the more useful examples. And because many of you that are looking to work in Internet of Things or cyber physical systems, you will need to develop wireless sensors. And this is code that's very useful for a wireless sensor application because we are going to be acquiring analog inputs, a number of analog inputs, and relaying that information back to a central database, or at least a Python script where we could use that to route that, use the Python script to route it to a central database. Okay, so the objective is to activate all four ADC analog inputs. That's again D0 through D3 of a standalone XBee Series 2 radio, then displays the user the data to the user. Okay, first step. We need to define a function that translates an integer I to its binary representation as a string S. Don't think we need to provide much explanation here. Hopefully you understand how this conversion works. It essentially cycles through all the bits of the potential output and converts the integer to a binary string. So for example, if you had the integer, let's say 10, right, in base 10, what would that be in base 2? So do this in my head here. I guess it would be 4, 2 plus 8. So you would have 1, 0, 1, 0, right? You have 0 plus 2 plus 0 plus 8, which gives us 10 in base 2. All right. And so that's the type of conversion that it's trying to provide for us, is the conversion between a base 10 integer and a base 2 binary string. All right, next step. So this is the main executable. And the first thing we're going to do, like usual, is import our libraries. This time we're actually going to be using our DDO set param. We've been importing that function for several of the previous examples, but we have not used it. We are finally going to use it. Okay. Next step is to define the address of the target device or node. In this case, we're using a standalone S2 radio, and the address is provided here. Again, remember, you have to have the brackets, you have to have the exclamation point in order for it to process properly. It says use a try statement to enable the sensors. I guess I didn't actually use the try statement, but I would recommend that you do so. That way you can catch any exceptions that are involved or that come up. All right, next, we use the DDO set param in order to place all of those four inputs, AD0, AD1, AD2, AD3, into the ADC analog input mode. So that's here, 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 and here. If you recall, and we can scroll up just for a second, you'll see again that mode number 2 is the analog in single-ended mode of operation, and that's what we want. Single-ended just means that the measurement coming in is going to be referenced to ground, or whatever the reference voltage for the unit is. It's not going to be able to provide a differential measurement. Okay, so we call this command for D0, D1, D2, and D3. All of them have the same mode. All of them have the same address. Done. Okay, next, we we used the short version of the DDO set param, where we did not include and I don't really have room here, but we did not include the change input, which was the sixth or the last of the inputs. And what that means is that the changes will not be immediately applied to the radio until we call the write command as well as the AC apply changes command. Now, you can see why it makes sense to do it this way. I could have set change to true for each one of those four DDO set param calls, but then I would have been applying changes 4 times, which is less than efficient. And so what I can do is set all 4 of the parameters at once, or set all 4 of the parameters serially in order, and then apply all of the changes at once, which is what we're doing. So right here is going to be the write and the apply changes. Okay, so I have a lot of writing on the screen, not much room left, but this piece right here, inside of the orange, that's where we're actually going to be setting the mode of our outputs. Okay, next step. We want to use the DDO get param command to retrieve data from all 4 of the analog input channels. And so we don't need 4 commands in order to do that. Fortunately, we can just use DDO get param, appropriate address, and then IS. And so IS is the ID, which acquires all the inputs at once and stores them as the string called measurement. We display that to the user real quick, and then you can see we are going to unpack it using that struct.unpack command we used previously. The format or the structure is going to be a 12-byte string, and then we're unpacking our measurement value, and that gives us 12 bytes, B0, B1, B2, B3. Now, the question is, what's happening down here? This is where we're going to post-process and sort of parse the individual bytes as they are extracted from the measurement object. But how do we do that? In order to understand, we need to scroll back above. I'm going to have to use a PDF version of the notes. Unfortunately, it doesn't want to display my equations on the iPad, but no big deal. All right, so let's take a look at this. So the DDO get param with the address and the ISID, when applied to, I say smart plug, but it could be any Series 2 radio, generates a string called, well, we're calling it array raw data here. The length of this array is defined by the equation below. The length of array raw data is equal to the number of analog measurements made by the radio plus 6. Now, the reason for that, if you see here, is that there is a structure as shown in equation 1. We start off with a 1-byte frame, which is n sets. So actually, we're going to go down and list what each one means. So n sets is a 1-byte value that seems to be unused. I don't normally dive too heavily or too deep into these things. If there's a frame or a byte that's not being used and it doesn't really have an impact on what I'm doing, I tend to just ignore it. I mean, I think that as an engineer, you have to be very utilitarian and practical. And I don't want to say if something's not broken, don't fix it, but some of these parameters really don't need to be accessed. So we're not going to deal with that first byte. Okay, the next 2 bytes, the second piece here, is the data mask. So this is a 2-byte array that defines the status of all 8 digital input channels, either active or inactive. Note that only the second of the 2 bytes will contain any values other than 0 for a stock XBee radio. That's because of the number of available analog inputs. The first byte will define the status of input channels 9+, which do not currently exist. So the maximum value of the data mask for the stock XBee radio is going to be 00FF, which indicates that channels 9 and higher are turned off, and channels 0 through 8 are active. 1 1 1 1 1 1 1 1. Okay. The next byte is going to be the analog mask. This is a 1-byte array that defines the status of all analog input channels, active versus inactive. So it's possible that if you, let's say, for example, we have 4 digital input channels and 4 analog input channels. In that case, for the data mask, all 8 of the channels would be 1s because they're all active inputs. But the analog mask would only contain 4 1s because 4 of them are acquiring digital input. So you can see if you look at the difference here, you'll see that the first 4 channels, 0, 1, 2, 3, are configured to acquire analog inputs, and the last 4, or the second 4, are configured to acquire digital inputs. And this makes sense because we know that that only the first 4 channels are even allowed or even capable of acquiring analog inputs. So the maximum value of the analog mask would be 0f because you cannot get anything higher than 0, 0, 0, 0 and 1, 1, 1, 1. Only 4 analog input channels exist. Next. The next in line is the 2-byte data value frame. I apologize for not using the pencil. Again, the equation won't show up in Microsoft Word, and it's relatively difficult to use the pencil in PDF. So for this one little section, I'll have to just utilize the zooming. Okay, so data vals is a 2-byte array that defines the single bit measurements acquired from active digital input channels. The structure of data vals is similar to data mask with a maximum value of 00FF. Okay. And so this makes sense because in the same manner that we can set the status of those first 8 channels to 1, you could also use that same structure to determine whether the input is a 0 or a 1 if it's just digital. So next we take a look at the last piece, which is going to be the analog measurements. It's the last bullet down here. Okay, this 2-byte array defines the measurements from any active analog input channels. Now, the 2-byte array is going to be needed for each analog channel. So it's 2 bytes per active analog channel. So if we have 4 active, that means we would have 8 bytes there. So the maximum length of this array would be 6 plus 2 times 4, or 14. That's right, correct? 8 plus 6, yes, 14. Okay. Note that there may be between 0 and 8 bytes associated. Okay, we already said this. There could be 2 bytes. All right. Or they could be, yeah, 2 times 4. Okay. So now let's break down how to actually pull out those analog values. All right. So we see here, this is an example where if you exclude the dot, 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 we only have 2 analog measurements. So we have the sets, data mask, data vals, and then you start with analog measurement 0, analog measurement 1, and you keep going in that way. Now, everything else is relatively easy to parse except for the analog mask. That is the point in the code that we are at right now. We are, and we're going to talk about this in depth in a second, we are at the point where we have acquired the raw data. We need to pull out the analog mask and actually process those bytes 2 by 2. All right, so now let's jump back into the code right here. We were at the point where we were post-processing and trying to extract the values from the raw data that is returned to us. So right here, we have our raw data as a set of bytes. Now you can see in order to acquire our first measurement, which we're calling V0, we are going to, see if I can make this bigger, we are going to concatenate 2 bytes together, which will create a 2-byte array, and then use a Python function, the int conversion, telling it, also reminding it that it's a 2-byte array. And that will automatically take our 2-byte array and convert it into an integer, which you will see right here. Now, why are we using bytes 4 and bytes 5? Let's take a look back at our previous resource. Oh, it never wants to load it right away. Sorry. And so what you see is that B0 is our sets, B1 and B2 is our data mask, B3 is our analog mask, and then B4 and B5 are where our analog values begin. Now, this may conflict a little bit with what I had written here, but the data vals frame is not going to be included in here. And the reason for that is because we don't have any digital inputs defined. So the numbering here is actually a little bit off, where the analog mask is going to start at B4, B5, because we have no data vals, the digital values description. Okay, so we know that each one of the following 2 bytes, 4 and 5, 6 and 7, 8 and 9, and 10 and 11, each 2-byte frame will define one of the analog measurements. So what we're doing is converting them, concatenating them together and converting them from a 2-byte array into an integer value. So 4 and 5, 6 and 7, 8 and 9, 10 and 11, and that generates our 4 values. Okay, but this is an analog representation of the binary uh, described in terms of the number of steps that we have between 0 and the maximum. Okay, if we want to convert that into an actual voltage, which represents the voltage that we're actually seeing at those terminals, we have to use this conversion down here. Okay, where what we're doing is we are multiplying our voltage, sorry about that, by 1.2 volts, which is the maximum voltage that can be incurred, and then dividing by 1023, which is the number of steps between 0 and the maximum for our A to D converter. Sorry, yes, our A to D converter. All right, and so this makes sense because let's say, for example, up here at the top, if we were if we were reading a value of 0, it would spit out a value of 0 here. If we were reading a value of 1.2 volts, it would spit out a value of 1023 right here. So all of these values are going to fall between 0 and 1023. What we're doing when we jump from here to here is we're converting from this format, which tells you the step number, the quantized step number you're at, and then gives you an actual voltage. And we just run the same conversion each time. I didn't bother defining new variables, so you can see that I'm just using the same variables over and over. And then we're going to display these values to the user and call them inexecutable. Okay. Next step. We want to show the test results that I got. All right. And note, I already said this, the ADC, the analog input, may not exceed 1.2 volts. That's the maximum. And we can take a look at a comparison right here. So what do these graphs show? Probably a little bit too much information for us right now, but you can see that there's 4 different lines. There's the red, the blue, the orange, and the green. And on the x-axis, what we have is the actual voltage that was supplied to those terminals, which I measured just using a DMM or an oscilloscope. And then the y-axis, we have the value that we acquired, and I should probably write here via software. Okay. And as you would expect, it's a one-to-one relationship, very close. The output that we get via software is very close to the measured input. And so this is really the most important graph for our purposes right now, this one right here, just showing that our outputs acquired via software or just measuring it directly are approximately the same. These other ones are showing the percentage error. I'll let you take a look at those on your own, but I was actually preparing this data for a technical paper, so it's maybe not as important for us. But anyway, you can see that it acquires the voltages properly. All right. Last thing I wanted to show here is just my setup. I was only using one X2 radio because that's all that was required, and I was measuring the data using an oscilloscope. You could also use a DMM, but that's how I get the values that were on the x-axis. It was the oscilloscope measurements. And you can also kind of see where my connections were um, for the respective pins. That marks the end of our module on remote data acquisition via the XBee Series 2 radio. It's a really great example slash exercise, one that I think provides the foundation for developing all kinds of cool IoT and cyber physical system related projects. Obviously, anything where you're trying to retrieve data from a sensor and communicate it wirelessly back to some sort of a script where you could do more interesting things with it. Anything in that realm could be built off of the code that I provided right there. So we'll end it at this point, move on to some other topics, and hopefully you found that example really useful and